Joule-Thomson coefficient is 1.11 Kelvin per atmosphere. And these are thermometers. We've studied how to obtain these things before, and then we put so in order we can take those out of the empirical sign, not use them as function of pressure, and just have E star minus P. This, do that whole calculation, it comes out to be 41.19 joules. That's it. Therefore, delta H net, which is also delta H zero formation of CO2, is equal to minus 393.5 kilojoules, and then it's plus this 5.0419 kilojoules. So how big a correction is it for carbon dioxide? Not very damn big. And so rounding this off, looking at 393.51 kilojoules. And put squiggles over these. We get kilojoules per mole. So this is tabulated out. And that little excursion was to show you what mass and nations one has to go through to get put in this table. So we now have two non-elemental entries in the table. But yeah,
Is that supposed to be negative?
I can't quite read.
Is that answer supposed to be negative?
Yes. Oh, of course. Yeah. I'll do my bookkeeping. Is So we got two very important entries in our tabulation, one for water, one for carbon dioxide. With them, you can go a long way to fleshing out this table. So note, so in solutions, we have some vocabulary that we use. We talk about solids and solutes, and it's pretty obvious that we're talking aqueous solutions because water is a solid and if they get off in there, it's a solute. But non-aqueous solutions are solutions with blissful liquids. It becomes unclear which it doesn't matter. Naturally, it doesn't matter. So let's see how that works. Nonetheless, my convention is that I'm talking about a solvent specifically, usually water. I'll use a subscript. One for it. We're talking about a specific solute. Two, but I just so you'll recognize that as I get into it. Okay, so thermochemistry of solutions. Consider formation of a solution from its constituents. Each and what's the standard state? So we have the enthalpy of a solution. Notice is an extensive state variable. It's a function of the pressure and the temperature and the number of moles. species, just talk about a generalized solution now, of any number of constituents. Because this is a heterogeneous, because this is a homogeneous function in roll numbers of a degree unity, we know from Euler's theorem and from our own deliberations that this is equal to the summation of Ni times Hi bars. That's Euler's theorem applied to this, which is a summation of Ni times a partial of H respect Ni at P N. Standard states of this constituent solution. We have a standard state we call the solvent standard state. It can be applied to more than one constituent at a time. Sometimes, and I'll try to explain what criteria for that are, but it is pretty simple. H1, that will stand for a solid in the standard state. It's just equal to the entropy of the pure solvent, the same continuous. So if water is a solvent, then its solution in standard state is pure water. It's out of that standard state, it's in the solution, but that's the standard, that's its reference state. But if we have for mixing with alcohol, for example, like we did the other day, we could just as well call alcohol a solid, they were miscible. And both water and alcohol would use that standard state. Pure water for water, pure alcohol for alcohol. That worked fine. But what if we're dissolving sugar in water? And we can use, then pretty clearly water would be the solid, and the standard state is pure water. What's the standard state of sugar? Pure sugar? I don't think so, because you can't have pure sugar in the liquid phase at standard temperature and pressure. It needs to be in the same phase with solid out of the solution state. So that's a different standard, and it goes like this. H2R0 is equal to the limit of H2 bar as the concentration or as the number of moles of species goes to 0, or as its mole fraction goes to 0, or as its mole fraction of solvent goes to 1, or it is equal to H so it's a very, very dilute solution. And it is the state in which each soluble molecule is interacting only with solid molecules. There are not enough solid molecules around to make this case. So those are things we want to tabulate. We define a new function, the intensive state function, called a relative, or sometimes we'll allow we call it L, species I, and that is just its partial Minuses, more enthalpy in pure state. And so that L1 bar, H1 bar, H1 0, L2 bar, H2 bar, H2 0 for relative low impact. So let's make up this solution, and we'll just solution for that in AFA plus HBB plus the solution at T0 delta H is equal to H in the solution minus H of the components, pure state, and that is just equal to summation bar. It is summation of these for the product minus summation of zeros for the reactants. Pretty standard stuff. And consider a binary solution, simplest solution we can have. And A is our solid, subscript 1, and B is our solute, subscript 2, and we have N1 moles of A plus N2 moles of B, forming a solution N1 A of N2 B. Solution to that. Temperatures of our standard tables. We have delta H of solution called delta HF, formation of solution, and it is equal to summation of mu I HI bars, and that is equal to N1 times H1 bar for the solid plus N2 times H2 bar for solid times N1 times H1 0 for the solid minus N2 H2 0. And we can rewrite that as N1 H1 bar minus H1 0 plus N2 H2 bar minus H2 0 bars N1 L1 bar plus N2 L2 bar. We'll roll it. When we get about this. Delta HF is called the Christina formation. Of a general solution, binary in this case. Now, special case. Left side, left hand 2, number of moles of solid, T1. And then then we have delta H of formation becomes just N1 L1 bar plus 1 mole times L2 bar, and we call that delta H of the capital S.
Can you scoot the paper to the right? There you go. Thank you.
Okay.
Yes.
Delta H capital S, and we call this the integral. Each solution.
Forming a solution with 1 mole solute.
The nice thing about this is measurable by calorimetry.
Just obviously say go to the calorimeter and whatever portion you are and reduce the data to effectively 1 mole solute and measure each of the solution.
And what do you see? Lo and behold, about delta H of capital S versus N1. That's the one we're bearing. N2 is constant.
What actions add compounds form a solution?
Temperature stay constant always.
You know, sometimes it gets warm, sometimes it gets cool, sometimes it stays constant. And that affects, after the calorimeter, what we're talking about here. And so there are two possibilities.
If we have delta H, if the heat solution is positive, that implies heat flow to the system, right? That implies that this is in the thermal process. We can have delta H S negative, that implies exo process. And both of these happen.
And you see it in the laboratory. If you pour sulfuric acid in water, what happens? You gotta be careful doing it because it's low heat. And you take ammonium nitrate and put it in water, you get close. That's pretty dramatic in case of sulfuric acid and ammonium nitrate. Usually very small, but nonetheless, they're measured.
So these curves, we've got some information that hopefully gets tagged in our table. Okay, now then 1 mole of A plus 1 mole of B forming solution, which is B in 1A solution minus delta HS. We can always write
These are enthalpy equations by putting the
negative of the change in enthalpy out there. P0, P0. Delta HS is equal to N1 L1 bar plus, I'm going to write this in, otherwise they sort of get in trouble with our units. L2 bar. Now I said this is an experimental quantity. So we've got delta H at S, which is N1, and I just will draw something here.
not the reason to do an experiment. From the units.
Okay. So we're talking about this particular solution. And I'll call it N1. This is delta H S at N1. So we can measure, we can find, but what we really want to know is the slope of this line, tangent. The slope plus the slope times L1 bar. Well, you look at this equation up here, and we can see that that intercept must be 1 mole times L, which is going to be L2 bar at N1. That's for a solution to that concentration. Right, so the intercept here is 1 mole times L2 bar at N1. That is read right off the chart. And the slope is L1 bar. So that produces our L2 bar, L1 bar. Whoa. And so from this, we get L1 bar is H1 bar minus H1 0 bar. H1 bar at N1 is equal to the slope at N1. And the limit, that's N1, goes to infinity, so it gets dilute in sodium. But H1 bar is equal to H1. Well, again, that is just H1 0. Slope goes to 0, and all left over is just H1 0. But the intercept, you see what happens here. The intercept at dilution is equal to, what is that? That is clearly equal to L1 mole, L2 bar at dilution. That's 1 mole times H2 bar 0. That's a standard state minus H2 squiggle to 0. All that. So H2 bar 0. This is standard state. The solute. Sometimes we call it H2 aqueous, aqueous solution. And it's read right off of this intercept. Intercept extrapolated to when this line is extrapolated, it goes out. Ultimately, it suits us so dilute, pour more water and make it more heat effective. Certain. So it will change. So from that intercept, of that extrapolated line, you get this limit, which is tagged H0 R0. So that's the stage for how we do it. For one, now we need an example to try to drive this home. Okay. Calculate the standard molar enthalpy for the sulfuric acid, aqueous,
What's that word you had underlined?
intercept.
Intercept? Okay.
Intercept.
No, the next one. Yeah. That one.
From lists
Lists. Oh, okay.
or tables. Might be in the back of your book. Go back and you'll find H2SO4 in there, you'll find aqueous sulfuric acid. And we're trying to find out where that number comes from. You look at do that, and then you can imagine where those come from, and then you can use it to take some confidence as part of your science. All right. Well, H2O2 aqueous is equal to delta H zero formation. This from the syllabus. Each understand state. That's the way we. As the art we made yesterday, how to determine the standard molar enthalpy of anything. You start with zones and standard state. So, for example, you have 1 mole of hydrogen gas, and we have 1 mole of sulfur solid. Sometimes you might find tables where they write sulfur as S8. You do that, you just take an 8 mole on that. Your textbook doesn't do that, not just all of the plus 2 moles of oxygen gas. Equal 1 mole of gas for the infinite minus delta H 0 formation. And this is what we were tagging. We can get that, we can find it. So we have H2 bar 0 is equal to delta H bar 0 formation is equal to summation of mu I HI zeros is equal to, let's write it out. We have 1 mole so 4 minus part of these. This is 0, 0, 0. Delta H formation, just like we said. So that will give it to us, but we can't do that directly. You can't take those elements and combine them and make that state directly. So, by some indirect path. Okay, well, step 1. Let's burn the solid sulfur to get sulfur trioxide. Burn the P1, get sulfur trioxide. Well, sulfur exists in 2 crystal modifications at ordinary temperatures. So the one is like diamond and graphite. One is more stable together. The stable state of sulfur is alpha crystal application. So alpha form, and that's called a rhombic crystal form. So rhombic sulfur is the standard state. We begin with that, and we're burning 3/2 oxygen gas, and we make SO3 gas. And we get released through these surroundings a heat flow of 395.72 kilojoules as our standard temperature pressure. Step 2. Step 2 was you hydrate. This gas we just made, so we SO3 gas, and we combine with water, liquid, and we get pure H2SO4 liquid, and we get 132.4 joules of energy flowing as a heat flow to the surroundings. By the way, this one here, tabulate. It's minus H0 of SO3 gas. There's another entry in our table, or minus 395.72 kilojoules is the standard molar rate of SO3 gas. So now we add. Step 1 and 2, and we get sulfur. We're just adding these up and canceling out what we can get sulfur gas. So we get sulfur plus 3/2 oxygen plus H2O liquid. That's good sulfuric acid. If you do that, add those two together, you get 528.16.
Can you shift the paper to the left? We can't see the. No, the other way. There we go.
Your left. Yes.
Yeah.
Yes.
It's
Ah. Right, got that. Okay. All right. So let's play the game again. Delta H0, 1 plus 2. Those equations up there, steps 1 and step 2. Summation of U high H high zeros is equal to 1 mole times the standard molar enthalpy of pure liquid minus minus 1 times the standard molar enthalpy of sulfur alpha minus 3/2 mole times the standard molar enthalpy of pure oxygen minus 1 mole times the standard molar enthalpy of liquid water. Now this one is 0 and this one is 0 because those are elements. Of course, it's equal to minus 528.16. molecule for water, which we got yesterday, divided by 1 mole. Then we get minus 8.3.99
We lost you.
kilojoules
Cool.
per mole. And so we tabulate this. But as the standard oil of liquid, pure sulfuric acid. That's not what we want. We want it in water. We've had enough water to turn the gas into the molecule next to us before, but we got to add some water now, make it very hot. Measure that heat effect. Set. Measure LHS the integral. Heat the solution versus number of moles of solid. And extrapolate. And get the dilution. Because that's where we'll find this partial mole quantity we're looking for. Now sulfur, when it dissolves, obviously exothermic, big heat flow to the surroundings, so that's a negative in the system. Just zero. This comes out here. And extrapolate back to this point. And this is 1 mole times L2 infinite dilution. That value, and that is equal thermally to minus 92.58 kilojoules. So that minus 92.58 kilojoules is equal to 1 mole times H2R 0, that's a different dilution, minus H2 0 pure sulfuric acid. So H2 bar 0, that's that infinite dilution. Solve for that is equal to minus 92.58 kilojoules, and it is plus this one here is that minus 8.3.99 kilojoules per mole, which is top on the dope. So it is plus minus that, minus 8.399 kilojoules. Per mole. This is divided by 1 mole. The whole thing turns out to be minus 909.27 kilojoules per mole. And that is a standard lower enthalpy. Going back, you're going to look it up, you'll find sulfuric acid, pure stuff with this number. You'll find sulfuric acid aqueous, that means there's a dilution with this number. But we're not quite through yet. Why? Because sulfuric acid is a strong acid. All acids within the ocean are strong, in the sense that 100% associated. But sulfuric acid associates substantially at moderate concentrations and completely infinite solution. And is 100% ionized at infinite dilution. So we have this changes, take a look at. Lost elevate here. Well, it's obviously zero because these are the same thing. That's not a change in state, also changing notation. Sulfuric acid in the ocean is this. These are the same. And this is zero. So we tabulate. Well, it does. Consequently, we have H R 0 for aqueous is equal to minus 9.927 kilojoules per mole. That's supposed to be equal to H bar 0 H plus. If we apply to this, at least plus aqueous, plus 1 times H bar 0 of SO4 minus 2 aqueous. So how do we make this relation? I said we had as many arbitrary decisions to make as we had elements in the chart, right? There's one more. Because sometimes molecules ionize, and we do chemistry with them ionize, and we have to allow for that, so we need either to choose the electron or some ion, like a hydrogen ion in solution, a hydroxide ion in solution, a sulfate ion in solution, or something, and assign it a value. So what's the choice? It's always a hydrogen ion, a solvated hydrogen ion, which is assigned it a value, and then all of the ions are relative to it. So by convention, we let standard molar enthalpy of the hydrogen ion of the aqueous ion here is in solution, so let it be 0. Then we tabulate this as the same as this as minus 9.927. And that's what you find there as well. So if that made any sense at all, you can see how we can flesh out fleshing out our table.
So my question is, before we had gotten the molar enthalpy as negative 813.99. That is it without.
Pure liquid.
Okay, and then
The following one, the negative 909, that's when it's
When you
infinitely
dissolve it,
dilute.
When you take all those molecules and surround them by water molecules, then you've got this infinite,
Okay.
which is found from the calorimetric experiments on dilution. Okay?
So, our tables can be fleshed out a little bit. Matter of fact, if I trim this out here, maybe, yeah. So this will be entries by similar methods. And then we read this. Take HCl gas. We could determine that with calorimetric. Or the HCl aqueous, how do we do that? Just slop it in water. Measure the heat of solution. Calculate the infinity and you get some correction. Good. So then if we know that one, then we do that, how do we get Cl minus aqueous? Well, this one must be this H plus Cl minus, and this one is 0, so that one has to carry all backwards. And then sodium chloride, we slop it in water and measure its heat of solution. Here it is. But it's ionized, so how do you get Na plus? Take this and you subtract off the chloride, which you already found. Na plus, this is H bar 0 of NaCl aqueous minus H bar 0 of Cl minus. You just put it down, right? So then, you take sodium hydroxide, dissolve that in water, sodium hydroxide solid, you measure its standard enthalpy by calorimetric. Dissolve it in water and find out what happens. And that's, if in that dilution, that's all sodium ions and hydroxide ions. We now know the sodium ions, so we find the hydroxide. And you can escape that. Oh, here's some other things I'll add on here. Some new entries in our database. Sulfur is an element, the standard state is 0. But in this monoclinic state, here's a phase diagram. Generic phase diagram of the substance, pressure temperature diagram, has those features. When things have more than one crystal modification, things get interesting. So if we just took out all that, you can see the same thing that I've drawn. But take out this line and this line, see the same thing. Well, here's 25 degrees Celsius to 98 Kelvin in 1 atmosphere. So that's the standard state of sulfur in the aromatic form. Over here in the monoclinic, you'd have to heat it up to above 95 degrees Celsius for the monoclinic fractionation. Then you keep heating it to melt. Mentioning this, we'll play a little game. Sure. So consequently, we could take the heated combustion of the aromatic, the heated combustion of the monoclinic temperature system is going to be a heat transition, just changing the problem in the monoclinic form is small, but there it is. We use this value for burning it all the way to SO3. Burn it under limited conditions to SO2, get H2SO4 liquid came from, we saw where the aqueous came from, we saw where the ion came from, and we saw where the H plus. Those some things that we have in fact talked about. Now, we have to make use of the tables. Well, if you had a table with, 10,000 acres, how many chemical reactions could you find in each reaction? Probably a whole hell of a lot. Some you can carry out, and some you can just imagine. Yeah. So tabulating data is very useful. Sad thing about human condition is that because collecting this colorimetric information is very, very tedious. And it's like they have quoted before, chemists are notorious for using any kind of estimate that they can put a new country made into, turn a crank, push a button, and all that on top of it, it spits out some charts and spreadsheets all about. They do that at the Cal Center. But if you're not going to do the hard work like calorimetry, they got it big. So sadly, when years go out, say now 4 or 5 times magazine to use that to solve all the problems. Good luck trying to find the data. Because not that much back. Still some stuff. So suppose we want to know what's the delta H of standard delta H in this reaction. Suddenly, plus benzene. No, that's not what we'll do. We'll take 3 of these and put them into those. There you go. Well, we got tables, these are in tables. It's just equal to summation UI, HI0. So it's just equal to the standard mole enthalpy of benzene. That's 1 mole times that. 3 moles times the standard mole enthalpy of summing. And come up. This one is 2.6.73. Mole. And the benzene, the adjustment was at 49.0. So you put those together and multiply them out, and you get minus 631.19 kilojoules, not kilojoules per mole. So that process is exothermic, but you can't take submarine molecules and say in benzene. You can't take that out. Have some fantastic habits. So using the tables is pretty simple. You probably know that since high school days. Now we're going to turn our attention to exploring in a little more detail what happens when you're not at the same temperature, you're not 25 degrees Celsius. Already laid the foundation of this. That temperature on heats of reaction. Ozone is that well, pressure. This is the summation of U high, H I bar, respective temperature, constant pressure. And this is summation of U high times C P I. Oh. And this is just delta Cp reaction. And so consequently, E delta H is equal to E delta Cp, delta H constant pressure. If we integrate these, get delta H, T1, T2, T1, T2, delta H T1, T2 rather is equal to delta H T1 plus the integral delta Cp T2 T1. Straightforward. In order to do this, you have to know the heat capacities of all the reactants and all the products. Fortunately, these are calculated about as much as the other from calculated, which isn't very much along the side. If during this transition from T1 to T2, any one of the reactants or products undergoes a phase change, you got to include that heat transition. Excuse me. For small temperature changes, you could just say delta Cp, delta T. But economically, you have to do more. So as an example, I'm going to look at effective temperature on the Haber process. For synthesis. Ammonia. Arguably, the most important chemical reaction in Hitler. Got good things and bad things. Learning how to fix nitrogen directly from the elements was a remarkable process. Well, let's say change stages. 1/2 moles of nuclear gas plus 3/2 moles of hydrogen gas, 1 NH3. It's also gas. It's plus 46.11 kilojoules at 1.5 degrees centigrade max. So the delta H at 298 K, guess how much? Minus 46.11 kilojoules. It's not kilojoules per bleeding mole, it's just kilojoules for that reaction. The heat of formation of 1 mole of ammonia is 46 minus 46.1 kilojoules per mole. Alright. So delta H, say 400 K. I mention this because that reaction just, when we study kinetics, we'll take a look at this a little bit. Maybe you didn't say well. That reaction just goes way too slowly. As a matter of fact, we measure it slowly at room temperature. So speed it up, the reaction be sped up by raising the temperature. But as you raise the temperature, you see this, this reaction is actually permanent. You raise the temperature, what's going to happen? When it's equilibrium, it's going to shift it back. This direction is going to lower the yield. Right? You usually get some yield at higher temperatures because of the rate. So it's a trade-off. How high do you raise the temperature? And also to increase
increase the yield is by increasing the pressure. If you've got 2 moles of gas here going to 1 mole there, so just squeeze it, cut it, and cycle law will confirm that these are all correct observations. So it's an important reaction, still running higher pressure and higher temperature. We're looking only at the temperature effect here today. We're going to heat that. You might say, well, why not run up to 1,000 degrees? Well, because by then you turn that, keep putting it back so far, you're not going to get it again. How will we,
We know that, we need LCP equals off, and it's equal to the heat capacity of ammonia minus 1/2 heat, 1 times this minus 1/2 mole times heat capacity of nitrogen minus 3/2 mole times heat capacity of hydrogen. And so supposedly we just estimate this. Because that's all we want to do is find out how to use this information, not get around with a bunch of significant figures. We can estimate it by just guessing at what these heat capacities are. Couldn't we? 2 of them are diatomic gases. How much vibrational energy do you think nitrogen and hydrogen have in there? So the heat capacity, constant pressure, both those gases should be, the heat capacity, constant volume for each of them is 2/2 R for 3/2 R for translation and 2/2 R for rotation. So that's 5/2 R at constant volume. Get the constant pressure, you add on another R, so it's 7/2 R. So let's just say they're both 7/2 R. How about ammonia? Well, it's a nonlinear molecule, so it's got 3/2 R for translation and 3/2 R for rotation, and it's got some vibration, not a hell of a lot, because those hydrogen are real pussy. So let's neglect that as well. So let's heat capacity of nitrogen and hydrogen are both 7/2 R. Now, assume heat capacity of NH3 is 3/2 R for translation, 3/2 R for rotation. So that's just
Maybe 8
and
halves.
then we add R, yeah, then we add R for heat capacity constant pressure, so it's just 4 R. Yep. And then you just see that delta Cp turns out to be minus 3R. And we assume that's a constant, and then we can say, well, delta H at 400 is approximately delta H at 298 plus delta Cp L2, might as well assume they're constant capacities. You see how easy it is? You can put the numbers in and show that this turns out to be minus 46.11 minus 2.54 kilojoules, and that's minus 48.65 kilojoules. So let's see. Now, one last thing. We'll have time to get through this, so I can catch up tomorrow and let y'all just do it on your own. There we had no phase changes to deal with. Here I'm going to give you some numbers. We're going to look at this process. Take sulfur in alpha form and oxygen, SO2 gas, minus delta this number's tabulated, I've got that written down in the chart. Back there somewhere. And we want to do this at a higher temperature. But it's high enough that now we're going over to the beta form. Plus R2. That's O2 gas. Minus delta H D2. And this one, I think I'm asking you correct. As well. And this is one more on what it is. So this is 400K and 100. Alright, so we know that this is delta H calorimeter. It must be equal to delta H T1 plus here is delta, here is the integral of Cp of SO2 times BP. That's one way to get there. Another way to get there is to go here. In this route, what is this? This, we have to stop off here and go from alpha to beta at temperature of transition, which is 296.83. All right. So going this way, we warm the alpha form up to transition temperature, and that takes a certain amount of energy. Then we transfer it to the transform to the beta form and heat transition to enter in there, and then we warm the beta form up to the final temperature, and then so think about that a little bit. I'll put something on the board for the first 6 of them off. And then we'll get